slowly decrease in charge.
Yeah, so that's what you've explained right there is a capacitor in an AC circuit. So that was all correct. So
Cool.
I'll just draw it here again real quick. That's what you said, since
Yeah.
I actually didn't start recording right there while you were explaining that. So yeah, you've got
Okay.
you've got your power source. Yeah, I forgot to turn on the recording. And then you've got your capacitor, which I'm pretty sure that's the symbol for it. I could be wrong.
Yes.
It
Yeah. No,
is, yeah.
that's because it's two plates that are spaced together, spaced apart. I'm sorry,
Yeah.
specifically in a certain distance.
And they've got usually some sort of insulating material between them most of the time. And yeah, like you said,
Yes.
for an AC circuit, the current is going to go one way. It's going to build up a charge on one side, and then when the current reverses, it's going to go back around in the other direction. The current will never actually pass through it except for like in tiny minuscule amounts. So for an AC circuit, you can put a capacitor in there. It'll actually, from what I understand, it will help prevent spikes from happening. If it tries to spike in a certain direction, as long as it doesn't exceed the rating for this, it should prevent any kind of weird surges. Now, in a DC circuit, if you've got just like, say, a battery and a capacitor, the outcome is going to be a little bit different because the power is going to try and flow in just one direction. And so what will happen is that charge will build up on one of the plates and it will effectively just stop.
Right.
There won't be any actual effective current flow through the circuit.
So what the fuck's the point of a capacitor on a DC circuit?
I don't know, actually. I'm not sure.
It's like how Nate was saying earlier. Those capacitors are typically used to help filter voltage. If I remember this correctly from my old job, they're kind of help to filter out like voltage spikes to make sure it's like a protection for certain components like chips and small drivers and things like that. If you look at a circuit board, like a control board for a VFD, you'll typically see microchips, and they will be connected to a capacitor, which is connected to a diode, or vice versa.
I mean, I get the AC thing, and I can understand that. But with DC, the current will stop at the capacitor and it wouldn't go past it. You'd essentially break the circuit, wouldn't you?
Yeah, I'm not really sure what they would use that for in a DC circuit.
Well, so in a DC circuit, usually, like I said, these are connected to chips and stuff, and those chips will actually the circuit. God damn it! If and granted, this is all on my trash memory, so I could be totally wrong. Please do your own research and prove me wrong. But if I remember this correctly, the circuits would branch from the capacitor to different legs of the chips, which would bypass the bypass the capacitor at certain moments in the circuit. It's very weird, and I don't remember all of the specifics. So sorry if that's poorly explained or wrong, but that's how I remember it. But I could be wrong.
So they kind of have like an open-closed bridge across the capacitor?
Well, like a capacitor will always have space between them, but in a DC circuit, half the time we would see these capacitors, and it would be like it could fit on your pinky, and they were ceramic that had their plates in them, and the whole point was to filter voltage. It would just filter voltage. It would how did my boss explain it? It help get the noise out of the voltage. Yeah, that's what I remember. If I had a
Yeah.
good relationship with them, I would ask, but I don't.
You were asking me something earlier, Nate. My internet cut out, so I have no idea what you asked. I heard, "Hey Corey," and then bruh.
Oh, that's where you went.
Yeah, my internet cut out.
Oh,
It'll probably
okay.
do that every time.
What lessons have you completed so far?
I've done lesson 2, and I've started lesson 3. I've read up to chapter 5 in my book, and watched a whole bunch of episodes of that guy online.
Okay.
Oh,
Let's.
Nate, you sound so disappointed.
Sorry, Nate.
It's all good. Where should I start then?
Oh
Like,
no.
honestly, every time I've looked at this shit,
Let me take
I've
a quick look and see what the learning objectives were for lessons 4 through 7, because I'm pretty sure some of it was just really simple stuff.
I have lesson 4, 5, 6, and 7 pulled up, Nate, if you want me to just read those.
Yeah, sure.
All right, so lesson 4 is first learning objective is to define capacitance, its use of measure, and the factors that affect it. Explain the exponential charge of a capacitor connected to DC, and explain capacitive charge based upon capacitance, resistance, and time values. So Corey,
sorry.
do you know any of that?
I have a general understanding of capacitors just based on the videos I've watched, but I haven't read anything in the book on it yet.
Yeah.
I think I'm on. I could tell you. I mean, this probably won't help Nate understand. Oh fuck, understand where I'm at, because I don't know if he's seen these videos. Probably not, because I don't think he needs them.
No, Nate is what we call a genius and doesn't need this kind of shit. But at least he's not a dick about it like a lot of other people.
You just
I
realized.
think I know who you might be referring to.
Oh, shit balls. What else?
Anyway, tell you what, why don't I go through and cover all of these learning objectives? I'll focus on those, and then if you guys have any questions, I'll do what I can to answer those.
For me.
Okay, does that work for you, Corey?
Hey man, it's your time, so whatever works for you works for me.
Okay, so first learning objective was defining capacitance. So capacitance is literally just the capacity of a capacitor. Pretty straightforward. Its unit of measurement.
Is a farad.
Yes, that is correct.
Yes.
One farad. I'll just write this down as I go. So capacitance is measured in farads, and the abbreviation for it is just a big letter C.
And
oh wait, hold on. Wait, no, I'm sorry. C is
me up already.
Farads is just literally an F. F for farads.
Yeah.
Yeah.
F for farad. C is for capacitance.
Yeah. C is capacitance. Yeah. C is the abbreviation for capacitance. F is just the abbreviation for farads.
And that's a capital F.
Yes.
Right? Because,
yeah. Capital F.
Yeah. Lowercase f is shit.
Lowercase f would be frequency.
That's what it is. There you go, Nate. Helping me live.
And then, right. So one important thing is that one single farad for a capacitor is a really high number, especially for calculations. Usually, your capacitors are going to be like in the range of microfarads, and the abbreviation for micro is this little thing. It looks just like a U. It's that little symbol. So microfarad would be this. And specifically, one single microfarad is going to be 0.000 0.001 farads. So it's basically 1 times 10 to the power of -6. So you can just count the number of decimal points. It's 1, 2, 3, 4, 5, 6 right there.
Yeah, Tyler, I was on episode 11 in your little videos.
Cool. So we're about the same there. Nate, I don't know if you have checked those videos out, but if there are concepts that you don't understand, you should definitely. I posted the playlist in the group, and
Okay.
for anybody that watches this that needs more additional help, that playlist is 26 videos of straight up, as basic as possible AC theory from very beginning. You don't know anything to learning AC theory. So
Cool.
sorry to interrupt, Nate.
It's all good. So one thing I was wrong about just a little bit earlier was the symbol for the capacitor. It's not this.
What?
The symbol
I
for a
thought it was.
capacitor, one of them is going to be curved, and the other's going to be straight like that. So that's your proper symbol right there for a capacitor. Let's see. The other learning objective was the exponential charge. Let me see where that was again. There was a formula for getting the charge. Actually, you know what? It's probably right in my homework here. I'm pretty sure I noted that down.
That's the inductive reactance formula. Is it T equals R times C?
Yeah, so that is for getting the time constants for so you remember how I mentioned before in a DC circuit it would just build up a charge on one side and eventually it would hit its maximum charge?
Yeah.
Yeah, so that formula right there, that T equal to R times C, that is your that's your time constants. I believe. Let me just double check and see if that was either the length of one time constant or the total time.
Let's see. So T equals R times C. I have it's question 24.
Yeah,
and
that's
lesson
actually the one
4.
I'm looking at right now.
Okay,
So,
cool. So
yeah, so that
takes
is
five time constants, right?
yeah. So one 5 time constants. Yeah, so it's just like with those other previous formulas that we used with time constants. It's 5 time constants to hit maximum charge. So yeah, if you wanted to figure out how long it took for a capacitor to fully charge, you would take T is equal to R times C to get one time constant, and then multiply that by 5 to get your total time. With R being your resistance and C being your capacitance. So time constant equal to R times C. It's pretty straightforward. Now, as for getting your capacitance, oh, that's on. There's a symbol in here. I don't remember.
Sorry, guys.
What's that? There's actually one single symbol on my notes here, and I don't remember what this was. I didn't write it down.
Write it down. We might know.
It's a large capital K. I'm not sure what that was.
Kindness, maybe. Kilo.
It's one of the values in a formula for capacitance.
The symbol K is no, we haven't gone over Coulomb's law.
I wonder if this is something I just grabbed out of the book and wrote down and didn't use. I'm starting to think I didn't actually use it for this homework assignment.
Yeah,
Yeah, it looks like I didn't actually use it for this homework assignment.
I keep finding things in physics for Coulomb's law. I'm just Googling it.
Oh, so one other formula that you might need, and this is just a simplified formula for getting flat surface. Give me a second here.
But it said the time constant thing was t equals r times d times 5.
So if you want
No,
to
it's t equals r times c, and that's one time constant.
yeah,
and then for your max charge, it's that times 5.
Yeah, so whether it's figuring out how long it takes for a capacitor to fully charge, or whether you're trying to figure out how long it takes for, like maybe the voltage in an AC circuit to hit its maximum voltage, it's always going to be measured in a length of 5 time constants, and specifically for the capacitor, one time constant is this, your resistance times your capacitance. And if you need to figure out your capacitance, if it's not given, one potential formula you could use is...
Are you downloading something?
What's up?
I think he's talking to his wife.
Oh, okay.
Sorry, my net
That's all good.
fucking shit.
So if you take the
It's probably
charge divided by voltage, your charge in coulombs, then you can calculate your capacitance. Although I don't remember if you actually need to use that formula for this homework assignment or not.
Never seen that formula before.
Okay.
Yeah. See here. I wonder why we use a different symbol for capacitors, because
I'm not really sure.
like yeah, I don't have a formula to just find C. Surprisingly.
I think these formulas might have been used in one of the next assignments, I think.
Maybe lesson 5 or 6.
Okay.
Oh, okay, Nate. That symbol that you used for capacitors, that symbol is used when it is a polarized capacitor.
Okay.
That's what that is. That C is polarized.
Oh, looks like we just lost Corey.
Oh no, you might want to pause the recording.
Oh, he's back.
There he is. Yeah, I looked ahead in lesson 5. It showed that.
Okay, tell you what, why don't we skip on ahead up to lesson 5 then? I think we more or less covered the learning objectives for lesson 4 here.
Cool, man.
You all good for jumping up to lesson 5, Corey?
Corey.
Looks like he's still having connection problems.
Rough.
I guess we can go ahead and move on ahead then. I'll be uploading this anyway.
Which is, I mean, yeah, that's solid.
Okay,
He made noise.
Lesson 5.
I synced it.
Describe the basic construction and operation of capacitors. I kind of just went over that already.
Yeah, we did that in the beginning, didn't we?
Oh, right. One important thing to note. So that space between the two plates, that little gap there, little separation, whether it's air or like ceramic or glass. That is called your dielectric, and that's a term you're going to need to know.
If Greg puts it on the test, yeah.
Probably will. I mean,
No telling.
there's going to be some questions about dielectrics too. And then various types of capacitors. Let's see. I know that's directly.
We have
within-
polarized and unpolarized.
Yeah, I'm trying to remember. There were some specific types. There were some.
There's oil-filled caps.
Yes, oil-filled
that.
capacitors, and then I believe there were also ceramic capacitors too.
Yeah.
Sometimes you can get. Oh, right. So sometimes you can get an instance where current will actually successfully flow through a capacitor, which is basically just when it's failing and breaking down. And that's just referred to as leakage.
Yeah.
Real straightforward term, nothing fancy or anything for it.
Which makes sense if you visualize the electrons moving through.
Yeah. And then, yeah, like you mentioned, there's polarized and also non-polarized types of capacitors. And the non-polarized ones you can use in either type, AC or DC, apparently. I wonder how the non-polarized one would work in a DC circuit, though.
They just don't give a shit.
Oh, okay.
Yeah, like it seems like it should be more complicated than it would be, but I remember looking at the board and it being labeled and then having a capacitor and that I'm replacing and it not having a positive or negative, and I'd look at my boss and go, "What do I do?" And he goes, "Solder it on there, it's fine. If it's not specifically polarized, then it doesn't matter."
Wouldn't it then just inherit the polarity of the circuit at that point?
Yes, that's what would happen. Hello, Corey. Welcome back.
Thanks. Sorry. Start shutting shit off in my house so my internet would work.
Turn off your phone.
My phone's actually dead.
Oh, well,
Yep.
I'm glad I could help you.
Kids got mad because I turned off the TV. I told them they can go play.
Okay, so I think that's all of the learning objectives.
I think so, actually. Let me take a look here.
Work safely with circuits containing capacitors.
Basically, shut off the power, more or less.
Yeah.
And make sure that there's
Oh,
not like a
man.
charge remaining on the capacitor too.
So
yeah,
I know you
discharge
probably-
the circuit and discharge the capacitor.
I know you
Yeah.
probably explained this, but what's the C equals Q over E? Capacitance
Oh, right.
equals-
So the C equals Q over E. I don't know if you'll need to actually use this or not, but if you're not given the capacitance of a capacitor, you can take the charge of it and divide it by the voltage, and you can get your capacitance.
Okay.
I don't
That
know
might
if you'll
be
actually
something-
need that formula or not, but it's there in case you do.
That might be something in lesson 7. I don't know. Like I said, that's one I haven't done.
Possibly.
Uh,
Hey,
let's
I
see.
found that formula that's got the big capital letter K. It's in
Yeah.
lesson 6. I'm not sure why I noted it down all the way back in lesson 4. So yeah, we are using that formula for something.
Oh shit. Okay.
Okay, so working with capacitors that are in series and or parallel. The learning objectives for those is explain how capacitance acts on a circuit when its components are connected in series, parallel, or in both, and then mathematically solve for total capacitance in those circuits. Now, luckily for you, some of it is very similar to the old formulas we'd use for, resistors in series and parallel. Give me a second here. I just got a text or something.
Tell him we said hey.
Oh, sorry. No, just random email. God, there's more
Popular man, Nate.
random emails.
Hitting up these chicks on Tinder, huh?
Everyone wants a little bit of Nate.
Yep. Big dick Nate.
Nope, just junk email. Okay, so let me look at my notes here. Okay, so for series circuits, total capacitance, it's a little different. So for series, let me just write this down here. If you want to get total capacitance, normally for most items you'd have in a series circuit, you just add them all together. But for series capacitance, it's the inverse formula. So 1 over CT, your total capacitance is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3, so on and so forth. It's the inverse formula.
Or we can use the negative one, right?
Yeah,
It's
or the
same
negative
thing.
one. It's basically
Yeah.
the same formula that you would use for getting resistors in parallel.
Yep.
That's what you'd use for capacitors in series. And then as for your total capacitive reactance, so XCT, or capacitive reactance total, is going to be equal to basically just take the individual capacitive reactances and just add them up. Because this is effectively a type of resistance. And you'd calculate it the same way, like so.
Although in that video I was watching, they were saying that with the, I don't know, that with the capacitors, that if you increase the capacitance and the frequency, the resistance goes down. That was weird.
Let me see. Hang on. I wrote notes for those.
Does it?
Give me a second.
Let me check and see.
Yeah. Let's see. Boop, 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 boop.
It's one of the more recent videos I watched, so hopefully I didn't remember it wrong, but I'm pretty sure.
Let's see. If we're looking, so if current goes up in a circuit, if we increase the frequency, current goes down, which increases the opposition to our current. So if we increase our frequency, the opposition to the current is increased.
Oh, there's a
with
formula for that.
Yeah, you're thinking of inductive reactance, Corey.
Mm,
And then see, yeah, capacitive reactance. If we increase
Oh,
the capacitance,
yeah, sorry, capacitive reactance. Yeah.
yeah, if we increase the capacitance, we increase the current, which decreases the opposition to current flow.
yeah, that's what I said.
Yeah.
I just found it odd.
Nate wrote the wrong formula.
Damn it, Nate!
You can use this one.
My poor eraser.
So XCT can be equal to 1 divided by 2 times pi times your frequency times your total capacitance.
Awesome. See, those videos are right. Yay. Oh, I found something that doesn't suck. I'm sorry.
Sorry, not sorry.
I just don't want to suck at this, you guys. I really appreciate the help.
I don't want to suck anymore.
I blame Roland. Hello? Sorry.
Okay, let me
Okay.
see if there's any other important formulas.
Yeah, if you can just load my ass up with formulas like fucking steroids, that'd be great. Cause I'm just
It's
gonna
always the math that fucks me over more than anything.
Oh, right. So for parallel, your total capacitance is just going to be straightforward C1 plus C2 plus C3, so on and so forth.
So the rules are just switched when it comes to capacitance.
Yeah.
In series, we use our parallel rules, and in parallel, we use our series DC rules.
Mhm.
Cool. If I were Roland, I would just play those YouTube videos that I found in, in class.
Let's see if there's anything else.
Lord.
Don't think you'll need that.
What about the inductive capacitance in parallel?
Inductive
But this-
capacitance?
Is that the same formula?
What?
We're on capacitors.
What is inductive capacitance?
The XCT formula for series, isn't there one for parallel, or is it the same one?
XCT. Oh, yeah. That's capacitive reactance.
Oh, sorry.
Yeah, there is one formula that I got for that.
Isn't that just 2 pi FC?
That's what I meant to say, but again, I was up till midnight last night, so we're gonna go with that.
I'm probably wrong.
The formula that I've got is that inverse formula. T is equal to 1 over xc1 plus 1 over xc2. That's the formula that I've got for parallel.
Total capacitance of parallel caps is calculated the same way as the total resistance of series resistances. Yeah, I have all the formulas for finding total capacitance of series capacitors. Caps in parallel have the same voltage drop.
Oh, so a little thing to note. So this formula here for total capacitive reactance, you could use this same formula to just get the capacitive reactance of a single capacitor. So you could just get XC is equal to 1 over 2 times pi times your frequency times your capacitance. That's another formula right there. Just for any single capacitor just by itself.
Yeah, that's you're talking about number 13, right? That circuit. Because that's what they do. The first thing.
Yeah.
Yeah, the first thing they do is get it for.
Isn't that the same formula for the series capacitance total? Or am I reading that wrong?
That the XCT equal to 1 over 2 pi FC. That's used, period.
Yeah, this formula will work for either series or parallel.
If you do the homework, it'll show you examples.
Yeah, but you said the XCT is for total, but then the one you just wrote down looks to be the same.
This will work for just an individual capacitor, this formula here.
Uh-huh.
You see how he didn't put T
Yeah, see
next
how
to it?
the difference between
Oh,
this one and
I
this
remember.
one is that this is capacitance of the single capacitor, this is the capacitance of the whole circuit.
Honestly, couldn't see that T. My resolution is
Oh, yeah, sorry.
it's
I
shit
still gotta
balls.
get a better webcam.
Oh no, it's probably my internet too.
It's
Sorry.
Corey's internet.
My webcam is a little shoddy too. It's kind of old.
Bro, I can't believe you're not doing this in 8K. What the shit?
Yeah, you should just screen share your VR. Go.
That was cool. Not gonna lie.
It was
When you
fun,
did-
but it wasn't treating my laptop very well.
Oh man, like it was awesome, and honestly, like that's how Roland should teach. That's how all these teachers should do this shit. Is just, you know, VR whiteboard.
Give him a virtual classroom.
Well, yeah, dude. I mean, his pictures are potato quality, and he just expects us to be okay with it.
Okay, I'm gonna go ahead and move on up to lesson 7.
I just want to make sure I understand this right. I'm sorry. So like in number 13, this circuit, you know, we're looking for the total capacitive resistance. So I have written down here step by step. And it says XC1 is equal to 1 over 2 pi FC3 for some reason, and I don't understand why. Why it shows. No, okay, so I wrote this down wrong. I'm an idiot. That's
Okay, so
everything I just asked you. Yeah, I'm sorry. That was my fault.
oh, I'm just looking at 13. Okay, so do you have this down then, or?
Yeah, no, I wrote down the wrong thing. I'm just an
Okay.
idiot.
Okay,
That's yeah, that's my fault, not yours.
I actually
or
got this
any-
one wrong too.
It's kind of weird. I fully expect to see a problem like this.
Yeah, no, I'm sure this will show up in the test.
Oh yeah, no doubt.
Which one are you guys looking at?
Lesson 6, question 13, the very last one.
It's where you've got 2 capacitors that are in series, and then you've got two capacitors in parallel with one more in series beyond
Yes.
those, and you're supposed to figure out the total capacitive reactance of that circuit. And the trick is, you know, it's pretty much the same as what you would do if you had resistors. So you would take the 2 that are in parallel and figure out what their collective capacitance is.
Then treat it like a series after that.
Yeah, and then treat it like a series.
Okay. What is the NF? Is that that's not the micro. What the hell's the N for?
Nano.
Okay.
Yep, that
Like a
N is
dumb
for
micro.
nano. That's nanofarads.
I have that sheet where all those stupid things are that I wrote them down somewhere.
Dude, this is some shit. Like, because in the field, everybody uses online converters. Nobody knows all of this decimal bullshit. Like, nobody. They all use converters. It's trash.
Yeah, micro was. Let me just write it down for you real quick. So micro was.
No, I've got it wrote down. You don't have to.
Okay, you got it all down. All right. Forgot.
Yeah, they're in my notes somewhere.
I'll tell you
but I
what.
know
It's
For
on
anybody,
that
for anybody
Golden
who
Bob
watches
sheet.
this video later, micro is 10 to the power of -6, and then after that it was
Nano was 10 to the power of -9.
Right. That was just a little n, right?
Yes.
Lowercase n.
You're
Yeah, so
really-
lowercase n, nano, which is 10 to the power of -9, and then after that was pico, right?
Yep, 10 to the power
Pico,
-12.
pico, whatever. Lowercase p, was it?
Pico, yeah, lowercase p.
Yeah, lowercase p. Okay, and that's
It's on the Golden Bob
10
sheet,
to the -12.
page 2 of 4. If for whoever's listening or whatever. I don't know if my audio gets recorded in these or not.
It does.
Uh-oh.
Oh,
I actually had an issue with the last couple recordings. I had your guys' volume up way too high.
Oh,
But I've tweaked it on Discord now, so it should come out okay.
okay. If anybody's listening to this, I'm very sorry.
and fuck Roland.
Yeah, dude, for real. I can't wait to graduate just so that I can be like, all right, man, I'd tell you it was fun, but it wasn't. You suck.
All right, so for the formula for getting, because I'm attempting to solve this question half here. So for the total, fuck, never mind. I think I done fucked it up.
Do you want to just do this circuit, Nate?
Yeah, that might be good.
Okay, give me a second here. And let me. I have to go back to it really quick here. I'll make up an example problem and then we'll run through it.
Much
Yeah,
obliged.
don't use those values because I mean, I have the answers right here, and that's trash.
That's
Alright.
trash.
It's trash, dude. Like I'm not gonna learn shit if we just do everything this way. It's trash. I will fuck it up.
All right, so here's our AC power source.
Don't you yawn at me, young man.
Sorry that.
One capacitor here. It is in series. We've got two that are in parallel. All right, so our power source, we'll just make up some number. Voltage, let's just say the voltage is 60 volts.
Okay.
And we'll say our frequency is, I don't know, 100 hertz?
Bro, what the shit?
What?
What country uses 100 hertz?
I don't know. I'm just making it up as I go here. Example problem.
I'm just
Natelandia.
fucking with you, man.
All right, and then for our capacitances, we got C1 here. We'll just say C1 is like, I don't know, 300 nanofarads. And C2, we'll just say that one's like 80 nanofarads, and then C3 here, and then we'll make it like 50 nanofarads. So we want to get the total capacitive reactance, and the trick to do that would be to try and figure out. We can start with this first capacitor here. Our formula for capacitive reactance is this one right here. So it's a simple matter of plug and play for the first one. It's going to be 1 divided by 2 times pi times our frequency of 100 times our capacitance. Now this is in nanofarads, so we have to make sure that we input this right into the calculator. We have to input it in terms of like actual farads for the calculation.
Tricky little bastard.
Yeah, we have to use the fucking crazy decimal
Yeah,
instead of using an online converter.
So in the calculator, I'm inputting it as 300 times 10 to the power of -9. Because it's 300 nanofarads, and nano is 10 to the -9. So
I'm gonna write those down because it's a nice little handy cheat sheet.
So taking our values and plugging it into this formula for capacitive reactance, we can figure out that XC1, our capacitive reactance of this capacitor, is equal to roughly 5,305 ohms. So we've got the capacitive reactance of 1, but now we need to get the capacitive reactances of these two here.
Hey Nate, before you keep going,
Yeah.
are you using the pi symbol on your calculator or
Yeah,
not?
I'm using the pi symbol.
Okay, this is what we call civilized bullshit. Some civilized ass shit right here.
I just use the pi symbol because it's a lot more shorter for me to do that rather than 3.14159, whatever.
How did you get 5,305 ohms? I got 0.000188496.
Sure,
Or did
maybe you put something in wrong on the calculator? Let me double check
I
my
don't know.
calculator really quick.
So 300 times 10 to the, and then you put
It's
that.
300 times 10 to the -9.
Yeah, that's what I did, and I got 0.0000003.
Oh, were you talking about just writing this in its farad form?
Well, no, like I was just making sure I did that right first. But so then it's 2 times pi times 100 times 0.0000003. Oh god damn it! I'm an idiot. I didn't put it under the 1, guys.
That's
Look,
probably why. So if you
whoever's
put all of
listening,
that under the 1, you should come out to roughly this amount here.
whoever's listening, just don't do what I've done, okay? If you don't do what I've done, you're fine.
How do you do the damn custom exponents? I forgot.
That little TP looking thing.
Oh yeah, let me show you really quick. Okay, so if you wanted to write out that entire value, that capacitance in notation, so it was 300 nanofarads. So one way you can write that in, and I'm hoping you can. Are you able to see this
Yes.
well enough? Okay, so it's 300 times 10. This little TP thing here is basically saying to the power of, and then whatever number. So in this case, we put in -9. I'm gonna hit enter, and yeah, comes out with 0.0000003.
And negative, I can choose the minus, right?
Yeah,
No,
use
there's a negative
specifically
button.
use this. This means negative right here.
Ah, I had a feeling that I was fucking that up already.
Yeah, if you use the minus, I think you might actually get a syntax error.
Probably.
Let me check. Yeah, you'll get a syntax error if you do that, if you try and use a minus.
Right, so I've 1 over 2 times pi times 100 times 0.0000003, and I got 0.000047124.
You might have
I
put
guess.
something in wrong. Okay, let me show you exactly how I put this in on my
Yeah,
calculator.
because this is not
Okay,
going well
so
for
one
me.
1 divided by.
Yep.
At this point, I'll actually start. I'll start one of these rounded brackets, and then from there on, I'll do 2 times pi times our frequency of 100, and then times our capacitance, I'll always put, whenever I'm messing with anything that is being entered in scientific notation, I'll always put that in a rounded bracket just by itself, just to make sure that nothing goes wrong with the calculations in the calculator, because sometimes it'll do the order of operations differently and you might get some weird answer. So I've got two different rounded brackets going there, so I already put in that, so I'll put in 300 times 10 to the power of -9, and then that was my last value, so I'll go ahead and do 2 of those. And there's my output.
So that gives me what you've gotten. So what I'm gonna do now is I'm gonna write Nate's answer.
Now it might be easier if you just to make sure that you get the right values. It might be easier if you just write out this whole formula on paper and just substitute in values at a time, rather than trying to like shove the entire formula into your calculator all at once. Because I've personally screwed up a few times myself, so you kind of run a little bit of a risk of getting wrong numbers.
Yeah, I forgot to do the times 10 to the negative power. I was doing 300 to -9. That's why I got a weird ass number.
Okay, so I'm gonna go ahead and continue with this here. So
sorry, Nate.
Yeah, it's all good. No, I gotta make sure I explain everything properly here. So right, so we're going for total capacitive reactance. We've already gotten the capacitive reactance of this first one. Now we got to get the capacitive reactance of these two, which are in parallel with each other. To get that, the best thing to do is, since they're in parallel, we need to find out what their collective capacitance is, so we can treat it as if it were just in series as one single capacitor. So going back right up here,
they add together, right?
We can, yeah, you literally just add them together. We can use this formula right here for these two. So the total capacitance of C2 and C3 is going to come out to 130 nanofarads.
And then we just use the same formula, right?
Yeah, so C2, 3, 30 nanofarads. And yeah, like you just said, we're going to use that same formula right up here to figure out what the capacitive reactance of this is now. So XC2 and 3 is going to be, let me punch this in here, 1 divided by 2 times pi.
A lot.
I'll let you guys calculate this real quick too before I spin up the number.
Yeah, hang on real quick, man. I'm trying to see. Okay, so I figured out what I was doing wrong originally. So if you, instead of putting it in scientific notation how you did, if we take it back to the farad number of 0.0000003.
Yeah, if you input it in decimal form, just like raw decimal instead of scientific notation, that'll work fine too for the calculation.
Right, but if you don't put it in parentheses, then it will fuck up, and that was where where the mistakes were made, and so I just wanted to point that out for anybody listening. If they don't do it the scientific notation way, the way you did it, then to make sure that you put anything under 1, your denominator, make sure that it's all in parentheses, or you'll fuck yourself. I'm sorry, so where were we at? Were we trying to figure out
right, so we got the total capacitance of these two capacitors, which was 130 nanofarads. So what you would want to do then is figure out what's the capacitive reactance now that we've got the capacitance of these two. We're basically
12.
treating this as a singular capacitor. Now that we've got the total capacitance.
Right.
12,242.7 rounding up.
What was that?
12,242.7 rounding up.
Yep. That is correct.
Hang on, so I brought 130 nanofarads into regular farads. Okay. So then for XC, it's just XC equals XC1 plus C2 XC23, right?
Mhm.
C. All right, hang on. I have to do XC23. Sorry, guys. 2 times.
Am I a fixer?
What?
My son. Apparently, they're talking about what I'm doing on my computer at the moment.
Kids are weird.
My wife was explaining it to him in broad terms, and he's like, "So he's a fixer?" Guess
That's
so.
cute.
I just fix shit around my house, you know. Yeah, that's the truth right there.
So XC equals 53,005.16477 plus 12,242.68793, and that math and stuff. Six, 4, 7, 7. All right. What was the answer you guys got?
We got 12,242.
Yeah, but that's XC23.
Yeah.
And then our XC total, I got 17,000. Let's see, 17,547.8527.
Hold on a second. Sorry, read that one more time for me.
17,547.8527.
Yeah, I just got 17,547. So yeah.
I left all my decimals.
Okay. Yeah, I'm just writing them down in whole numbers here. So yeah, that's how you do it. So yeah, like you just did right there, Tyler. We figured out our capacitive reactance of this one, then we figured out the capacitive reactance of these as if they were one singular capacitor in series with this one.
Right.
So we added them together. We looked at this rule, XCT, your total capacitive reactance, is just the capacitive reactance of all of them put together. So that one plus that one. XCT is equal to roughly 17,547 ohms, approximately.
Looking back on it, I feel stupid now. It's like the same shit we did last year, just different formulas.
Yeah, different formulas, different.
It's all
different
terminology.
Different
Like,
concepts, very similar formulas.
It really is, and it doesn't help that Roland doesn't really explain terminology that well. Corey, you weren't here the last time Nate and I got together for a study session, but Nate was just like, "Yeah, dude, I just read and plug in," and I just felt so stupid.
I just shove the book into my face and perform osmosis.
Ah, man.
Just sleep with it tonight, and hopefully I'll learn something.
Yeah, man. Us stupid folk out here, we learn with the shovel.
Fine, heating them tools.
Okay. Yeah, and that's the pinnacle of lesson 6. So,
Oh, that's
I'm
right. We
good to
still have
move
lesson
on.
7.
Yeah. Mm-hmm.
At some point before the end of it, if you could just, throw a bunch of formulas at me so I could write them down, that'd be great.
Bro, honestly, if you just go into the quizzes and click to the end, you can it'll give you the answers to all of them. What I've been doing is doing that first, and then writing them the entire question and process of how to do them in my notes, and it gives you all the formulas there.
Yeah, but I just prefer to, because I've been writing notes next to the formulas to know what they are and when to use them, essentially. That's what I've been
Okay,
writing as well. Because, I
I
mean,
get where you're coming from.
having the formulas doesn't mean no good if I don't know how to use them. Now, granted, as you say, I could go back and try and do some deductive reasoning on classwork, but he had a sheet earlier that looked like it had a bunch of them on there. Slap that bitch back down later.
All right. Lesson 7 looks like a lot of recap of all of the stuff that we've already covered.
Really?
Yeah, I'm just skimming back over it again here.
Because this isn't one I've done.
Lesson 7 is all about capacitive reactance. Let me skip over to the other side.
You like
That's
Okay,
what we
so-
just did.
Real quick, in a nutshell, since there's a whole lesson just for this one, your capacitive reactance is SC, or XC. It's a form of resistance. It is measured in ohms.
Yeah.
It's the opposition to current flow caused by, your capacitor.
Yeah.
Let's see.
You had it when the kids were outside last time.
And then, like I showed you before in, just the previous assignment there, and I'll write it down again. Your capacitive reactance, SC, for any given capacitor is going to be equal to 1 divided by 2 times pi times your frequency F times your capacitance C. And then let's see.
Yeah, Corey, if you've been following along with those videos and you've been doing the worksheet that guy has with them, that information is on the worksheet as well. I have that copied down.
Oh, yeah.
Man.
I've been listening to those mostly at work, with the exception of last night. So I actually haven't been writing those down, but I do know what tables you're talking about.
Yeah, man. Shit is cashola.
Reactance. A lot of this is just solved for capacitive reactance, just using that formula. I'm looking to see if there's anything else I need to actually show you. Sometimes you might be given a problem where they give you your capacitive reactance and then either your frequency or your capacitance, and they'll say solve for the missing value. And again, it's just a matter of plug and play with this formula. Let's see what else.
And then do some algebra level shit.
And then,
You're just moving things around.
Yeah, and then you might also have to look for your amperage as well. And just like how you would use your other formula, which was I is equal to E over R for capacitive circuits, you can use the formula I is equal to E over XC.
Right, we use XC
Instead
to find
of
our
R.
I. Because our XC is a form of resistance.
Yeah.
It's a form of opposition in the circuit.
Let's see if there's anything.
Did I say
else.
something smart?
Yes, you did.
What is up? Hell yeah, boys. It's me. Growing
Can you-
my brain back.
Can you use a pretty much similar formula for the inductance?
What do you mean the inductance?
For the fuck the God damn it, the squiggly line one.
The what? The inductor? An
There
inductive
we go.
circuit?
Yes, thank you. That one.
Oh, the formula for your inductive circuit is just XL equals 2 pi FL.
Well- I meant for finding amperage.
Oh,
Could you do the same thing there?
I'm pretty sure. Yeah. I'd have
I
to
think
look
he's
back at
right,
my
yeah.
notes. But yeah, I'm pretty sure that was also the same formula too.
Sorry, I didn't mean to sidetrack and
No,
confuse
that's all good.
pretty much everybody with my complete lack of terminology.
dude. Fucking hell, man.
Systems. Yeah, I'm not sure where it's at in my notes, but yeah, I'm pretty sure the formula was more or less the same for inductors.
Like we wouldn't have a meter in the field.
That's all mental math, man. I mean, obviously.
Fellas, I witnessed induction today. Like,
Firing between the neurons that gave you that great idea earlier.
yeah, man. Like pure hype. I'm hanging these lights, and the circuit's supposed to be dead, but we're treating everything as live. So I pull out my Widowmaker and hold up my Widowmaker to the wire, and it's running hot. And
Yep.
I'm like, what the fuck? And my journeyman, he's like, what do you think is happening? And I was like, is this inductance? And he goes, fuck yeah, it is. Go open the other box. Yeah, because I have been bitching at him about not fully understanding inductance. And he doesn't understand how to explain it to me.
So I'm guessing there was a box nearby with current going through it.
Yeah, dude. Yeah.
That's cool.
That wire ran into a junction box, and it was just using this J box as a pull box. And when I opened that junction box, and it was crammed full with wire, and I pulled that live wire out and put my tester up to the wire for my light, and it was dead.
Oh, okay, I got you. Because they're all crammed in there next to each other.
Yes.
Oh, that's cool.
Yeah, man. I was like, look at me. I'm learning stuff.
Yeah,
I wouldn't have thought.
I've been
about that,
shocked a few
actually.
times from induced voltage. Really, really
Dude,
low
it's
amounts. What was that?
I just said it's nuts.
Yeah, it is. Is there anything else you guys want me to cover?
Well, if lesson 7 is basically everything that we've done in lesson 6,
Most of it is
then-
that.
yeah, then I'm good.
Okay. You good, Corey?
Yeah.
You don't sound very happy.